Alright, in this presentation I will give you a short introduction to the Play Canvas environment and also how you can implement your own low-level VR experience. First off, what is Play Canvas? Play Canvas consists mainly of two parts, which is a MIT licensed web-based game engine for creating 2D but mainly 3D WebGL and WebGPU experiences. Alternatives there are Babylon.js, FreeJS, and so on. What sets it apart is its editor, which is the second part, which is commercial but has a really good free tier and is very Unity-like, meaning you have an entity component system, UI systems, an integrated asset store, and so much more. Alternatives there are like the Babylon.js editor, the Rogue engine, which is an editor for FreeJS, and of course you can also use web exports from Godot and Unity. But the real thing is, if you ever get to try the Play Canvas editor, you see what sets it apart. I mean, the main are features like scene setup, lights, cameras, and so on are quite obvious. But there are also project management tools like the possibility to share projects, to use real-time collaboration, and it also has an integrated versioning system. And during development, there's no real build process needed, which means you can easily debug all your scripts directly in the browser. And you also have a direct what you see is what you get experience for materials, lights, and objects because you develop right in the same environment. You also run your final application. And not only that, you also have live updates for a lot of things like materials, lights, setups, object positioning, and so on, but also for script attributes. Short interplay for who am I? My name is Wolfgang Rechberger. I'm the CEO and designer and developer of P&R Office for Experience Development. Our main tool are walking tours, including digital experience apps, which are offline capable PWAs, including AR, VR content, mini games, quizzes, and so on. But back to Play Canvas. We start our demo with a simple first project. Here you see like the my account where I start a initial project. Like you see here, there are some templates for AVE-Wall, WebXR, first-person shooter, and so on, but I really start with a completely fresh new project and open the promised editor. And I directly go into the integrated asset store to grab myself a Orbit script, meaning to implement a simple interaction with the camera. And then I grab the camera from the outline and add two script components to it, which the first script handles like the Orbit camera interaction in general, and then I add a second script which uses the mouse input to control this Orbit camera script, and then I press play, and with a few seconds I've created my first fully interactive 3D scene where I have a simple cube which I can present with an interactive camera. Then I show you the version control where you can easily create a new checkpoint, meaning a commit to the project, add a small description to what I did for this commit and create my checkpoint. So whenever I mess up with the editor or scripting or what else, I can go back to this checkpoint. Then I show you that you can create new folders, which is quite nice to keep your project in order. And there I drag and drop in a GLB or a GLTF file, which is like the standard version for using 3D models for web experiences. And I also automatically get my materials set up and a template which I can simply drag in, and now I already have my BOM in place. So if I now update my preview, or launch my preview, better said, you can see the model already in my scene. Now I fight a bit with the Microsoft Windows system, but what I wanted to show you is that we can now change the material of the BOM dynamically, and this gets represented in the live preview automatically and is updated on the fly. So I updated the position directly in the editor, and I also, change the normal bumpiness or the metal glossiness, and this is now completely represented in the preview, which is really, really nice, especially for designers, level creators, and so on. Another nice feature is that you can easily copy and paste assets from one project to another. So you can kind of create some, framework project where you keep very often needed used scripts. And here I simply copied a frame buffer picker example script from a demo, which kind of allows me to listen for object clicks um, on 3D objects, and another pulse script which simply animates if it detects a script, like you see here. Then I show you the editor where I open the pulse script, and the nice thing here is now I don't have to, get away from the browser experience. Of course, you can use your own Visual Studio, Visual Code, or other editor of choice, and sync them. But the integrated development experience is really nice. And now I added a small console.log. And the interesting thing is, like I said before, there's no, deploy, like mangling with your scripts during development. So I can really listen to or add a breakpoint for that. So I can really go deep into kind of, debugging processes you are used from your usual web development experience. So, sorry, I just kind of left my thing here. But let's now dig into low-level AR, VR. What is that all about? Why even bother with, implementing your own web VR or web XR stuff? Web XR in general, in my opinion, is the future, but it's not yet mass market ready. What do I mean by that? If you take a device like like any Quest, for example, then you really have all the features in terms of hit test, hand input, and so on, anchors, light estimation as well. The problem is that those devices are quite rare still. Also, like the Vision Pro of Apple was kind of a commercial failure. What you get in terms of adoption are, of course, smartphones, but the problem there is in terms of WebXR, there is almost no support from iOS. And also, I mean, I could, round about the whole iOS policy in terms of PWAs and so on. But if you take the Android world in comparison, it's not that much better because you have a wide range of devices there, and it's really not like WebXR features like depth sensors and so on are not uh, widely supported or integrated in terms of hardware. So what are your possibilities if you want to implement mass market web AR or VR features? There are some SDKs which kind of emulate WebXR, like A4, ZapWorks, Blip AR. They are great in terms of features, but they are quite costly. A4 now has, as far as I know, a bit cheaper pricing model, which is a bit beginner friendlier uh, than it used to be. But the main issue for our offline capable PWA is that all those platforms and SDKs are online only. On the other hand, there are some great open source libraries like ARGS, which does marker-based AR, image-tracked AR, or Mind AR, which does that, including also face tracking. Then there's what I call low-level AR, VR, and you can also go a different route like machine learning solutions of MediaPipe and TensorFlow.js, which are, for example, used by the Mind AR library. Low-level AR, VR, which is the solution I talk about today. What do I mean by that? First of all, I mean really low level in terms of reduced features. We only talk about 3 degrees of freedom, meaning only rotation in space, no movements, anchors, stuff like that, which is sufficient for simple applications and also has the advantage that it is quite beginner friendly for kind of AR or XR beginners. And low level also means that we really dig deep into the device APIs. Great about that is that they are good and broadly supported on iOS and Android, also really on old devices. And so we deal with the device orientation and screen orientation for VR. We map those rotations to the virtual camera. Then we will use the media device API for um, AR, meaning we use the camera image and you know put it into the background. And we also use full screen API, which is Android only. The great thing is that you could also kind of build your own effects, for example, for the camera image, and also use completely different user interaction paradigms based on these rotations. So when we talk about screen rotation and device rotation, screen orientation is quite straightforward, which is nothing else than dealing with portrait versus landscape mode of the device, which and gives you back 0, 90, inferior also 180 degree and 270 degree based on, if you have the device in portrait or landscape mode. Device orientation is a bit trickier because it gives you free orientations in space. I will try to show you that with that animation of beta and gamma. One catch there is that for iOS you need a specific permission request, and this request needs to be based on user gesture, meaning you can't simply do a onload permission request, but you have to put it onto a button, for example. And then we have free angles in space, and then simply map that onto a virtual camera, right? There is something like a set local Euler angles function for the entity, and then we push our angles there, and we are good to go, right? Well, not exactly. If we have rotations in 3D space, it's a bit complicated because there's the one solution which is based on Euler angles, um, where you have simply 3 rotations alpha, beta, gamma around 3 axes, and they seem to be logical and easy to understand. Um, but and also they are like the standard for sensorics output, and based on that also for the device orientation API. But the problem is that these Euler angles have a sequential character, meaning they are 3 mutually dependent rotations, and therefore the sequence of application is crucial, meaning if you have x, y, z versus z, x, y, you can come to a completely different result. And there is also our nasty friend, the gimbal lock. Gimbal lock is an originally mechanical problem with gimbal mountings, and in generalized form it's a loss of degree of freedom at sequential rotations, which happens if you rotate one angle in parallel orientation of a number, or one axis in, better said, in parallel orientation of another. And the thing is represented in digital systems as well, and usually if you have any form of rotation and you experience some kind of unstable behavior or some stuff where the rotation gets smaller and smaller and suddenly it flips, this is usually the indicator that you stumbled across the famous gimbal lock. Solution for digital systems, what can we do about it? Um, uh, but sorry, I will show you the animation first. There we have our three axes, and if we, orientate them parallel, we kind of lose the orientation possibility, which is called the degree of freedom for the green axis, meaning that we only can rotate it into 1 degree now. How can we solve that issue? One solution is to convert all three rotation into their respective rotation matrices and apply them. But even more elegant solution are the so-called quaternions. What are quaternions? Mathematically, they are a number range which extend the real numbers with 3 additional dimensions. I don't know if you have ever dealt with the imaginary component I, for example, around electronics or stuff like that. This is the same idea, only extended with 2 additional dimensions, j and k. And geometrically, they are 4-dimensional hyperspheres. And, if you hear something like 4D hypersphere, everyone is, what is that about? I give you a really, really short try to visualize the stuff. If we take something like a 2D sphere, which the layman calls circle, we have a 1-dimensional surface and 1 degree of freedom, meaning that every point uh, on the circle, like the surface of the 2D sphere, is defined with the angle alpha, and Pythagoras gives us kind of the way to describe uh, this circle. And if we extend that in with 1 dimension, we get a 3D sphere. Laymen call it a ball. And we have now a surface which is 2-dimensional, meaning that every point on the surface is defined by 2 degrees of freedom, alpha and beta. And we extend our circle formula with 1 additional dimension. And with this mechanic, we can go 1 additional step and we land at the 4D sphere, which is called the hypersphere. I cannot really give you a good visual representation of that, but the thing works similar like before, meaning we now have a 3-dimensional surface with 3 degrees of freedom, alpha, beta, and gamma, and we extend our sphere formula with 1 additional component. Another visualization, which is mathematically a bit incorrect but even easier to understand, is that if we take quaternions as a vector and with the additional scalar part, we have something like a rotation. So meaning that if we have this vector in space and a rotation, we can now build any kind of rotation in 3-dimensional space, only with the difference that we don't have, sequential rotations of individual components, but with 1 rotation around this free vector, we now have all the rotation data implemented. Show you also that into a small animation. We have like this purple vector and we rotate the object around that and we are ready to go. Right, in application you can think of quaternions as a special kind of transformation matrices which are only used for rotations. Therefore also sequence rules apply, meaning if you have some kind of parent and child quaternion transformations, you can combine them together and add them to or apply them to the entity. And if we have if we go back to our initial problem, the sequence is quite simple. We first of all build our initial quaternion based from the Euler angles we get from the device rotation API. Unfortunately, the order is a bit different than which we get from device rotation API. So we have to do a manual calculation of our initial quaternion and can't use the integrated quaternion set from Euler angles function. And also what you have to be aware of that you have to remap the naming of axes and also the inverted direction of the z axis, which is present in the convention of PlayCanvas, which is quite the same, I guess, also for FreeGS and so on. This is like the more heavy stuff, and then we build a simple transformation for the screen rotation and then multiply those individual quaternions, build our final quaternion, and then as a last step set this final quaternion to the entity and are ready to go. How does that look in code? Here we have kind of the device and sensoric stuff where the only difference between an iOS device and an Android device is handled because we need some kind of permission request for the iOS device. So if this device orientation request permission, which is only implemented for the iOS devices, we listen to that, and if this permission request is successful, then we add our event listener for the device orientation and also for the screen orientation, and store that in where is it? In the screen orientation and device orientation variables. Here you see the heavy stuff where we build kind of our first quaternion. We do that by storing some cosine and sinus values of these and build the formula for our initial quaternion. A second quaternion I forgot to mention in the slide before is that you also have to take into account that beta 0 means the camera flat on the ground, but that would be a different value than in PlayCanvas because angle 0 would be facing forward, and therefore you also have to build a second quaternion for minus p half around the x-axis to compensate that. And our actual third quaternion is now handling the screen orientation, and we always multiply our initial device orientation quaternion with all the quaternions we build afterwards, and as a final step apply these the resulting quaternion to our entity, meaning our camera. So that looks a bit theoretical. How can such an application look in a practical use case? I have a small bomb demo you can try out yourself, but I also have a small screen capture here where I simply launch it with a QR code and have in the initial state a touch-based game mode, but at the options I can enable the device orientation and also enable our camera so that you can also see kind of an image of my messy flat in the background, and you can go back and start your game experience, which is simply falling bombs you can detonate by touching them, and there are also some test sphere and test ground around that, And if you are too late, the bomb touches the ground, you lose a life. And yeah, that's like the most simple, the simplest gameplay I came up with. But I hope you kind of understand what the mess is about and what you can do with it. What are now possible next steps? You could also implement stereo rendering and barrel distortion and add something like what the cardboard did a few years ago. And another thing is you can also integrate the device motion API and possibly come up with some really floaty, hacky 6 degree of freedom tracking. Um, because like I said before, with the rotation API, you only have 3 degrees of freedom, which is enough for a lot of applications. Um, a few links mentioned here, like the quaternions. If you want to go deeply into their mathematical foundations, there is a great article out there, and another old article which you only unfortunately find at the Web Archive is really describing all the stuff I talked about here, again in detail: device rotation, gimbal lock, and so on. I hope you find that interesting, useful, and so on. If you have any feedback or question, don't hesitate and write me a mail. And other than that, I say thanks for watching.